We are going to discuss this chapter on gravitational fields. Learning outcomes. By the end of this chapter, you should be able to describe a gravitational field as a field of force and define gravitational field strength. G. We also call this the acceleration of free fall. Now, over here you will see that it is called gravitational field strength and it has the unit Newton per kilogram. We will see the details afterwards. Recall and use Newton's law of gravitation. Now, this is not one of the Newton's third laws, it's another law which is called Newton's law of gravitation. There is an equation for this. Solve problems involving the gravitational field strength of a uniform field and the field of a point mass. We will see what the gravitational field of a uniform field looks like and what the field of a point mass looks like. So you have to be familiar with uniform field and radial field. Okay, we will see that afterwards. Define and solve problems involving gravitational potential, psi. We use this Greek letter psi, psi. Analyze circular orbits in an inverse square law field, including geostationary orbits. Okay, by the way, this is phi, okay, phi, phi, not psi. Psi is another symbol, another Greek letter. Okay, previously we learnt about circular motion. Now we will apply that circular motion to these geostationary orbits. Alright, so here you see gravitational forces and fields. Now these people are falling in a uniform gravitational field. They are in the field of the earth, close to the earth's surface. But the further and further you go from the earth, the less and less uniform it becomes, the more radial it becomes. We will see what it means. And by the way, in your book, whatever is in green bold letters is very important. You have to know the meanings of these words. At the back of the book, you will get the definition of this word. You have to study the definition because in paper 2 they can ask you to write down the definitions of these words which are in green bold letters. For example, over here, gravitational field is in green bold letters. So you have to know the definition of this word. Okay, it's in the back of the book, the glossary. Study it and you have to write it correctly in the paper 2s. Okay, now we are looking at the glossary. You can see the gravitational field strength. This is the page. Gravitational field strength definition is given. The gravitational force experienced this gravitational field strength. Okay, by the way, you should know the meaning of gravitational field strength also, G. And you can see this is from the equation F equals ma. F is now W, the weight, A is G. So we get G equals F over m. The gravitational force experienced by an object per unit mass. Force per unit mass. That is the gravitational field strength. And by the way, we wanted to look at gravitational field. So here you can see a region where an object with mass experiences a force. So similar to magnetic field, gravitational field is a region where an object with mass will experience a gravitational force. Magnetic field is a region where an object, magnetic magnet or magnetic material experiences a magnetic force. That is a magnetic field. Similarly, we have the definition for gravitational field. Let's go back to where we were. Okay, this is how we represent the magnetic field. Gravitational field. Similar to the magnetic field, these are called field lines. We use them to represent the gravitational field and also the direction of the gravitational field. Now, the direction of the gravitational field is the direction in which the gravitational force will act. Okay, if you keep an object close to the surface of the earth or even far away, the gravitational pull of the earth on the object is towards the center of the earth. So therefore these arrows should point towards the center of the earth. They point along the radius of the earth. You can see this is like pointing along the radius of the earth. So therefore these are called this is a radial gravitational field. So if the earth is like a point mass like this, then the gravitational field lines are radial. And also you have learned that the further away the field lines are from each other, the weaker the gravitational field, or the weaker the field. Now in this case you can see, the further and further you go from the earth, the greater and greater will be the distance between adjacent field lines. So the gravitational field gets weaker the further away you are from the earth. The spacing of the field indicates the strength of the gravitational field. The further apart they are, the weaker the field. The arrows on the field lines show us the direction of the gravitational force on a mass placed in the field. Okay, and also in your book these bullet points are also very important. Okay, so this is the radial field, and here we have the uniform field. Now this is a gravitational field, so here we have a uniform gravitational field. If you consider close to the surface of the earth, the field lines are approximately parallel to each other, so therefore we get a uniform gravitational field. How do we know this is uniform? Because the distance between the field lines is the same. You can see distance between adjacent field lines are approximately the same. Therefore this is a uniform gravitational field. Previously we learnt about electric fields. There are three types of fields that you learnt about: electric fields, gravitational fields, and magnetic fields. In the AS classes we learnt about electric fields. Now we will learn about gravitational fields, and later on you will learn about magnetic fields also. But in the O-level classes you have already learnt about these three fields, and you also learn about uniform electric field and about uniform magnetic field. Okay, so over here you can see that these field lines are parallel to each other, and the distance between them is also the same. So everywhere over here the force on an object is the same. That means the weight is the same of an object anywhere in this field. It doesn't change. It will be the same because the field is the same, uniform field. But over here you can see, the further and further you go from the earth over here, then the gravitational field becomes weaker, so the weight on the object becomes weaker. But if you consider a point close to the earth, the weight doesn't change significantly of that object when you move away from the surface of the earth. Alright, now we have so this is called a uniform gravitational field, this is called a radial gravitational field. It's all given here. We describe the Earth's gravitational field as radial, since the field lines diverge, spread out radially from the center of the Earth. However, on the scale of a building, the gravitational field is uniform, since the field lines are equally spaced. Okay, so here we have Newton's law of gravitation. Again, whatever is in your book that is in these green boxes are also extremely important. These are again the definitions. It is important that you memorize the definitions with understanding, and then write those definitions in paper 2 when they ask you, because in paper 2 they ask you to write these definitions. And why we ask you to memorize and write it with memorize with understanding and write it is because if you try to write it in your own words, you might miss certain keywords that they are looking for in the definition. So if you miss those keywords, you won't get the full marks for the definition. That's why we ask you to memorize the definition with understanding. Any 2 point masses attract each other with a force that is directly proportional to the product of their masses and inversely proportional to the square of their separation. Now that is given by this equation. A statement of Newton's law of gravitation is shown below. So any 2 point masses, let's say the mass of body 1 is m1, mass of body 2 is m2. So any 2 point masses attract each other with a force, here is the force F, with a force that is directly proportional to the product of their masses. This is the mass m1, m2, so the product of their masses, because this is a multiplication, so you are multiplying these two, and you can see the greater the product, the greater the m1 or the greater the m2, greater will be their product and greater will be the force. Okay, so this is the gravitational force. Okay, it is on other words, it is the weight. Okay, so we will see how we get the F equals ma equation, W equals mg equation from this also. You move one mass here, then you get F over m1 or F over m2. That will be the g, because W equals mg, g equals W over m. So we'll see that afterwards. Product of their masses and inversely proportional to the square of their separation. Now this r is the distance between the point masses, between the masses. Okay, so over here the greater and greater the distance between the masses, so this distance is taken from the center of masses of the two bodies. So the greater and greater the distance between the masses, the greater will be r and lesser will be the f. But you can see this is r squared, so that's why we say inversely proportional to the square of their separation, because this is r squared, so we say square. Inversely proportional because it's 1 over that. Note that the law refers to point masses. Now you can see here it's important that you write these keywords like point masses, okay, or particles. Things are more complicated if you think about solid bodies which occupy a volume of space. Each particle of one body attracts every particle of the other body, and we would have to add up all these forces together to work out the force each body has on the other. Now you can see this is what I explained. So let's say you have so this is to explain this equation over here. Let's say we have two bodies, m1 capital M and simple m. The distance between the centers of masses is r, and any two bodies which have mass will exert a gravitational force on the other. So this F is the gravitational force acting on this body capital M due to the body simple m, this body. So this force here is the weight of this body due to this one. This body exerts a gravitational force on this, which is causing it to be pulled this way. This gravitational force is the weight of this, okay, capital M, we can say, times the gravitational field strength. That is the weight. This is the weight of this due to this. Similarly, this is the weight of this object or this particle or point mass, this point mass due to this mass. Okay, so this is the force due to this, because of this. This is the one exerting this force. This object here is exerting this gravitational force or weight on this body over here. Okay, so we can see this is what I explained previously. Force is directly proportional to the product of their masses, and force is inversely proportional to the square of the distance between the masses. And from this you can get this. You put everything together here, and to convert a proportionality into an equation, you have to add a constant with the equal sign. Now you can see here it's a proportion, here it's an equation. So what has happened was there is a constant with the equal sign, and this constant here is g. We call this the gravitational constant, also called the universal gravitational constant. This is a constant and it has the value 6.67 into 10 to the power minus 11 Newton meter squared per kilogram squared. Okay, this is also given in your data sheet that comes with your exam papers, but it's better if you know this. Anyway, you will remember this when you do a lot of questions. Okay, so you have to do so many questions that you will automatically remember this number. Okay, so we can use it for spherical objects like the Earth and the Moon. So any two bodies will exert a gravitational force on each other. Now maybe you have your book in one place and maybe your pen in another place. So even these two objects exert a gravitational force on each other like this. So let's say this is the pen, this is the book. So they will exert a force on each other like this, a gravitational force of attraction, and that is given by this equation, we can say. So we can apply it to the Earth and the Moon. This is the equation. So you should know this, you should be able to use this. Memorize the definition with understanding, remember the keywords. 2 point masses, then directly proportional to the product of their masses, inversely proportional to the square of their separation. Okay, so you can see what happens now. This is what I explained previously. The further and further you go from the surface of the body, massive body like the Earth, the greater and greater will be the distance between the adjacent field lines. And you can see that over here also. So say this is the Earth, and the further and further away you go from the Earth, you can see the distance between the field lines increases. So here distance between these field lines is this much, here it is even more. And you can see that the area quadruples when you double the distance. Here it's R, this is the area A, here it's 2R from here to here. So once it's 2R, this area quadruples. Okay, this area quadruples. You can see here 1, 2, 3, 4. Here it's just 1. Here it's R, so the area is A, let's say. When it's 2R, the area is 4 times A. And you can also see between the Earth and the person also there is a gravitational force of attraction. I told you any two bodies, between any two bodies that have mass, there will be a gravitational force of attraction exerted by one on the other. So this force over here is the weight of the man due to the Earth. In other words, we can say this is the gravitational force on the man due to the Earth. So this force is exerted by the Earth on the man. Similarly, this force here is the gravitational force of the man on the Earth. So this force here is exerted by the man on the Earth, and this is a Newton's third law pair. You remember there are about 6 criteria for a pair of forces to be a Newton's third law pair. First is they should act on different bodies. You can see they are acting on different bodies. One is acting on the Earth, the other is acting on the man. Then they should have the same line of action. You can see if you draw a line along this arrow, that line will also be, this arrow will also lie on that line. If you draw a line along this arrow, it will also be along this arrow. Then they should act in opposite directions. You can see they are acting in opposite directions. They are the same size. They have to be the same size. They are the same size. Okay. It's the same size. Even though one is small, the other is big, the size of the force on them depends on both of them. Now this force F is given by this equation. So it depends on the product of the masses. It depends on the mass of this as well as the mass of this, the product of them. So same size, opposite directions, same line of action. And there was one more. Okay, same time, it has to act for the same time. So again, for a pair of forces to be Newton's third law pairs, there are about 6 criteria. I have made another video explaining Newton's third law. In that I've explained using several examples of how a pair of forces can be Newton's third law pairs, and I have also explained certain misconceptions. So you can watch that video about Newton's third law. Okay, so you can see what happens to this. Also I explained that. Then then we come to the acceleration of free fall, also called the gravitational field strength. And by the way, this R is the distance between the centers of masses. You know, the center of mass of a person is somewhere close to the navel or belly button. Okay, somewhere behind the belly button, somewhere in that area. And center of mass of the Earth is in the middle. So remember, this distance R is from the center of mass of one body to the center of mass of the other body. Okay, gravitational field strength. Again, you can see this is in green bold letters. In the beginning, we went to the glossary and we went through the meaning of this word. Okay, so over here, what is more important is what is in this green box. Now, based on what is given in the glossary and based on what is given here, you can put the two together and give the definition. Okay, so if some point is here and there are additional points in the glossary, you can add it to this so that you have a more complete, easy to understand definition. Okay, so you might even see that what is given here is the same as what is given in the glossary. Okay, now we said meters per second when we said acceleration of free fall, but it is the same as newtons per kilogram. This is in base units. Newtons per kilogram is in SI units, which is not a base unit. But if you break it down to base units, see this unit and this unit, if you break this down to base units and simplify, you will get this unit. Okay, now how we get this unit? Because G is equal to W over M. Gravitational field strength is weight over mass. Now this weight is given by F over here, and this is in newtons, this is in kilograms. So then this will be newtons per kilogram, like this. Okay, and also it's an acceleration, so that's why we give the unit meters per second squared also for this. Now if the unit is meters per second squared, we call it acceleration of free fall. If the unit is newtons per kilogram, we call it gravitational field strength, but it is the same thing. If you simplify this to the base units, if you write this in base units and simplify, you get this. You can use this unit as also you can use this unit, but remember, if it's gravitational field strength, it's better to use this unit. If it's acceleration of free fall, it's better to use this unit. The gravitational field strength G at any point in a gravitational field is defined as follows. So again, very important, memorize the definition with understanding. You can add things from the glossary also, which has this the meaning of this word. The gravitational field strength at a point in the gravitational is the gravitational force exerted per unit mass on a small object placed at that point. Again, look at the equation when you go through the definition. The gravitational field strength G at a point is the gravitational force, that is F, exerted per unit mass. Now why it says unit mass is because when you divide this by this, you are getting the force for 1 kilogram, okay, or per unit mass on a small object placed at that point. So F is the gravitational force or weight on the object, and M is the mass of the object. Gravitational field strength has units of newtons per kilogram. This is equivalent to meters per second square. I already explained this. Okay, now you can see the Newton's law of gravitation. This is the definition. Here is the equation. Okay, so you learned Newton's first three laws. This is a different one. Okay, this is called Newton's law of gravitation. And over here, so we have this, and if you bring this simple M, now you can say capital M may be the mass of the earth, and simple M may be the mass of a stone. Okay, so let's say the stone is close to the earth and the mass of the stone is simple M. Mass of the earth is capital M. Okay, then what we have is F over, now you can bring the M to this side, or in other words, you can divide both sides by M. Now if you bring the M to this side, what you will have is F over M equals Gm over R square. F over simple M, this one, is equal to G capital M over R square. This is what you will get if you divide both sides by simple M. Now if it's let's say like the earth and the stone example, the mass M is for the bigger mass, okay, mass of the earth. Simple M is for the mass of the stone, the smaller mass. Now if it is in the gravitational field of the earth, then what you will have is, you know, this equation, G is equal to F over M, where M is the mass of the stone, F is the weight of the stone or the gravitational force on the stone due to the earth, and this is given by G, the gravitational field strength. Okay, so this is equal to Gm over R squared. Therefore we can say the gravitational field strength is the universal gravitational constant G times the mass of, let's say, the earth in the example of the stone and the earth, and then R squared in the example of the stone and the earth is the distance between the center of the earth and the center of gravity of the earth and the center of gravity or center of mass of the stone. Okay, so again it is the distance, R is the distance between the center of masses of the two bodies. Okay, so if something is on the surface of the earth, then r will be the radius of the earth, because if there is a stone on the surface of the earth, the distance between the surface of the earth and the center of gravity of the stone is negligible compared to the center of gravity of the earth, which is in the center of the earth, and the surface of the earth. That's a very large distance compared to the distance from the surface of the earth to the stone. So if it's something like that, we use the center of the radius of the earth. Okay, the radius of the earth, because which is the distance from the center of the earth to the surface of the earth, that is the radius of the earth. We use that in this calculation, because that center of the earth to the surface of the earth is a huge distance compared to the distance from the surface of the earth to the center of the stone when the stone is lying on the surface of the earth. So the distance to the center of the stone from the earth is negligible compared to the distance from the center of the earth to the surface of the earth, the radius of the earth. And you know what happens is, when you go further and further from the earth, let's say it's not a small distance where you are moving away from the surface of the earth, but if it's a large distance, something like this, let's say the stone is here, now it's going large distances, it's not moving a distance which is close to the surface of the earth. If it's moving a large distance, then you can see this r changes significantly. Okay, g is constant, mass of the earth is constant. Now again we are applying this for the example of the stone and the earth. So if the stone is moving significant distances, then mass is constant. So when r increases, g decreases. Okay, so when this doubles, this will decrease by a factor of 4. Okay, force is a vector quantity. It follows that gravitational field strength is also a vector quantity. We need to give its direction as well as its magnitude in order to specify it completely. Now you know the gravitational field strength, the gravitational force, they are all in the same direction. This applies not only to gravitational fields, any field. The direction of the field is actually the direction of the force. Now if it was an electric field, it is the force on a positive charge, because if it's a negative charge, the direction is the other way, not in the direction of the electric field lines. Similarly, if it's a magnetic field, it is the direction on a north pole. Now in the case of gravitational fields, you don't have repulsion, you have only attraction. Okay, so g is not a constant. We need to give its direction as well as in order to specify it. The field strength g is not a constant. It decreases as the distance r decreases. That's what I said. So if it's r is increasing or significantly, okay, when the object is not short distance from the surface of the earth, if it's moving very large distances, then when r increases, g decreases, or when r changes, g changes. It decreases as the distance r increases. The field strength obeys an inverse square law with distance. I already explained inverse square law, because when this doubles, this decreases by a factor of 4. So we call it inverse square law because of the square here. Okay, it's inverse because it's 1 over that. This is in the reciprocal denominator, so that's why it's inverse. And then because of the square, we say inverse square. Inverse square law. The field strength will decrease by a factor of 4 when the distance from the center is doubled. So when r doubles, g decreases by a factor of 4. I already explained that. Close to the Earth's surface, the magnitude of g is about 9.81 newtons per kilogram. Even if you climbed Mount Everest, which is 8.85 kilometers high, the field strength will only decrease by 0.3%. So you see, g doesn't decrease significantly when you are close to the surface of the Earth. Okay, but surface of the earth means we have to consider from the sea level, so it doesn't change much, but it changes significantly if the distance is such that the earth looks like a point mass. So if it looks this size, and if the movement is such that it changes the distance significantly, Okay, let's say it goes from here to here. Now you can see, compared to the size of the earth, this distance is very large. So therefore the g will change significantly in that case. But if it's close to the surface of the earth, small distances like 10 kilometers, 8 kilometers, then you can see when it is about 9 kilometers, this doesn't have a significant decrease. G doesn't decrease significantly because the change in distance is only about 10 kilometers. But if it was something like maybe 100 kilometers, 1000 kilometers, then it will be significant. Okay, so you can see from this equation, gravitational field strength G depends on M as well as R. Okay, if it's from the moon and the earth, moon and a stone, it will be different compared to earth and a stone. Okay, so the gravitational field strength G at a point depends on the mass m of the body causing the field and the distance r from its center. See worked example 1. Okay, so those are the two, because capital G is a constant. This won't change. It's a constant for the universe. We call it universal gravitational constant, and I showed you the value of that number. Okay, here is an example. It is very important that you understand these examples. If you understand these examples and theory, then you should be able to do these questions very easily. The earth has a radius 6,400 kilometers. The gravitational field strength on the earth's surface is 9.81 newtons per kilogram. By the way, you don't need to memorize this value. It will be given to you, but again, when you do a lot of questions, you will automatically memorize this, because these questions involve using the radius of the earth. Because when we take the distance between the center of the earth and object, you may have to consider the radius of the earth, which is from the center of the earth to the surface of the earth, then the distance from the surface of the earth to the particular object, center of mass. Okay, they have given the gravitational field strength, they have given the radius. We are supposed to determine the mass of the earth and its mean or average density. So write down, the first thing you can do is write the quantities given in the question, and if you can draw a diagram, that is better, but for this I don't think you need a diagram. Use the equation G equals gm over r square to determine the mass of the earth. You already learned this equation and I showed you how to derive this equation. It's given here. So using this law, Newton's law of gravitation, we rearrange it so that the simple m, we bring it to this side, so f over m, and then here this side you have g capital M over r squared. Then this is since this is f over m, that is g, then we get this gm over r squared. Okay, so g is 9.8. This capital G, they give you that value 6.67 into 10 to the power of minus 11. It's a constant, universal gravitational constant, and m is what we need to find. Okay, so for an object close to the surface of the earth, the gravitational field strength is 9.8. Okay, so assume this is for an object close to the surface of the earth, because we want to find the radius of the earth. So to find the radius of the earth, the distance is from the center of the earth to the surface of the earth, which is the radius of the earth. Make m the subject of the equation and you will get the mass of the earth. Now the equation for density is mass over volume. Remember, there is another part to this question. We found the mass, then we have to find the density. Assuming the earth is spherical, you know the volume of a sphere is given by 4 over 3 pi r cube. You should know this equation. It won't be given to you in the formula sheet. So you have to know the formula for surface area of a sphere and also the formula for volume of a sphere. Volume of a sphere is given by 4 over 3 pi r cube. The formula for surface of a sphere, surface area of a sphere is surface area of a sphere is equal to 4 pi r squared. surface area of a sphere is equal to 4 pi r square. Volume of a sphere is given by this. Okay, density equals mass over volume. Mass we found in the previous part. The volume we can find using the radius of the earth, which is given 6,400 kilometers. Substitute, you will get 5,500 kilograms per cubic meter. Now you should answer all these questions and check the answers after you do them. It's in the CD. Okay, also you can download it from the internet, and also we have it in our drive. Make sure you do these questions, because these questions in the brown boxes for every chapter should be done, because once you are able to do this, you have the minimum knowledge required to answer the past paper questions. Okay, so make sure you answer all these questions. Make sure you understand the theory, and if you have any difficulty answering these questions, go back and review the theory. Now, for example, over here, these questions here are based on what we learned before this. Even these questions here are based on what we learned before the questions were given. So what is based on what is in this chapter. So everything what we learned so far is tested by these questions here and these questions here. So make sure you do those questions, so that, and you should be able to do them correctly. Do them, check your answers. If you have any difficulty, go through the theory part and try to answer them again. You should be able to answer them, and also go through these examples, and make sure you over here you can draw diagrams to help you understand it better. You can draw diagrams and then do them. Now your answers have the solution. It's not only the answer, it has the solution. So if you look at the answers to this, it's not just the answer, it has the solution also. So there also an explanation is given how to answer this question. So you should be able to do that. But still, if you have any difficulty afterwards, you can ask me. It is very important, like I said before, that you do these questions, all the questions in every chapter, all the questions in the brown boxes. These are also called self-assessment questions, so that you have an idea of how to answer the past paper questions. So this is again the minimum knowledge required to answer the past paper questions is gained by going through the theory and answering these questions correctly. Okay, then the next one, energy in a gravitational field. Okay, so here we have you have learnt about gravitational potential energy in the AS classes, and you came across this equation: gravitational potential energy equals mgh. This equation, gravitational potential energy equals mgh, can be applied to objects close to the surface of the earth, because when it's close to the surface of the earth, the g doesn't change significantly. Okay, g is constant. But if we are considering so this approach is satisfactory when we are considering objects close to the surface of the earth. However, we need a more general approach to calculating gravitational energy for two reasons. Now this is what I explained earlier. If we use GPE equals mgh, we are assuming that an object's GPE is 0 on the earth's surface. Now you know at the surface of the earth the height is 0, so from that reference level we consider the gravitational potential energy increasing as you move it away from the surface of the earth. So at the surface of the earth, we assume that the object's gravitational potential energy is 0. This is fine for many practical purposes, but not, for example, if we are considering objects moving through space far from earth. So this is the important thing. Okay, so we can't really use this equation for objects to calculate the gravitational potential energy or gravitational energy of an object moving through space far from earth. But for objects close to the earth's surface where g is constant, we can use this. Now previously we saw that the further and further the object is from the earth's surface, the lesser and lesser will be the g. Okay, so g changes, okay, when it's an object moving through space far from earth. And also you know that when the object is much further away from the surface of the earth, or whatever body we are considering, when r goes to infinity, g goes to 0. So when r is a very large number, g will be a very small number. It will be infinitesimally small when this is infinitely large. Okay, so if we lift an object to a great height, g decreases, and we would need to take this into account when calculating gravitational potential energy. For these reasons, we need to set up a different way of thinking about gravitational potential energy. We start by picturing a mass at infinity. Okay, so now what happens is, a mass is coming from infinity towards, let's say, the earth. Now when it is at infinity, when the object is at infinity, now we are considering the earth and a particular object. Okay, so when the object is at infinity, r is very large, so the gravitational field strength is 0. But when it is getting closer and closer to the surface of the earth, r is becoming lesser and lesser. So then what will happen? This will become more and more. And when g becomes more and more, the gravitational energy that it has also increases. Okay, so what we can say is, at infinity the energy is 0, but when it comes closer and closer to the surface of the earth, it becomes greater and greater. Okay, so don't confuse that with this. Okay, this is for objects close to the surface of the earth, that we are moving by a small distance, so we are moving the objects close to the surface of the earth here. But the other one is for objects which are in space. Okay, for these reasons we need to set up a different way of thinking about gravitational potential energy. We start by picturing a mass at infinity, that is at an infinite distance from all other masses. We say that here the mass has 0 potential energy. This is a more convenient way of defining the 0 of gravitational potential energy than using the surface of the earth. Now we picture moving the mass to the point where we want to know its gravitational potential energy. As with lifting an object from the ground, we determine the work done to move the mass to the point. Okay, so from somewhere far away where the gravitational field strength is 0, you bring it towards the surface of the earth where you want to determine the gravitational potential energy of. So work done in moving the object from that point to the earth's gravitational field is actually equal to the magnitude of gravitational potential energy. So as with lifting an object from the ground, we determine the work done to move the mass to the point. You know, work done is equal to energy transferred. So when this object comes from infinity towards the surface of the earth, for example, then the work is done. Okay, it is equal to the energy transferred. But what is happening is, the earth's gravitational field will pull it. Okay, so what will happen is, the earth's gravitational field will pull it, and when it gets closer and closer to the earth, the gravitational potential energy increases, because the value of gravitational field strength G increases. So as with lifting, we determine work done to move the mass to the point. The work done on it is equal to the energy transferred, that is its gravitational potential energy, and that is how we can determine the gravitational potential energy of a particular mass. Okay, so the work done is equal to the energy transferred to it, that is its GPE, and that is how we can determine the GPE of a particular mass. Now you can see this about potential. The gravitational potential is 0 at unit. Now this is different from gravitational potential energy. There is no energy part here. This is called gravitational potential. So again, you have to know the definition of this. Don't confuse this with gravitational potential energy. Okay, we'll have a look at this diagram. Now you will understand why it's negative. The gravitational potential is 0 at infinity. Far from any mass. So if there is no gravitational field acting on a particular body, then the gravitational potential is zero. We can also say the gravitational potential energy is also zero, because G is zero, and decreases as mass is approached. So what happens is, when it gets closer and closer to the body, the magnitude of the gravitational potential energy increases, but we are using a negative value. So because when it gets closer and closer to the surface of the earth, the size, okay, without considering the sign, the gravitational potential energy increases. Okay, the gravitational energy increases, but also you have to consider this when it is close to the surface of the earth, right? Where in this way, now if you consider the surface of the earth, and when it is getting closer and closer to the surface of the earth, using this equation, the height decreases, so the gravitational potential energy decreases. Okay, that's why we have a negative value here. When it gets closer and closer to the surface of the earth, the negative value increases, the energy increases, but the negative value of it increases. Now we will see more in detail about this. This is something that some students have somewhat difficulty in understanding, but it is easy. Okay, so you have to compare it with this one, mgh. The further and further you move away from the surface of the earth, the greater and greater will be the gravitational potential energy. So if an object is coming out of the earth towards the earth, the energy, gravitational potential energy of it increases, but with a negative sign, because of this. Because when it is getting closer and closer to the surface of the earth, the gravitational potential energy should decrease. So when you use a negative sign, and if the negative value of it is increasing and increasing, then we can say it matches this equation, because the gravitational potential energy is becoming more and more negative. When the object is coming from outer space towards the earth, it becomes more and more negative. But the size of the gravitational, if you consider the number without the sign, that number increases. But if you consider the gravitational potential energy with the negative sign, because it's coming from infinity to the surface of the earth, we use a negative sign, and this negative number is becoming greater and greater. Okay, so we can say, in that way we can say the gravitational potential energy is decreasing when it is coming from infinity to the surface of the earth. Okay, so you'll understand this better. Okay, okay, so here we have gravitational potential. In practice, it is more useful to talk about the gravitational potential at a point. This tells us the GPE per unit mass at the point. Okay, so when you say gravitational potential, something is divided by the mass, because we get per unit mass. Okay, now when we say gravitational potential, you will see that it tells us the GPE per unit mass, gravitational potential energy per unit mass. So the gravitational potential energy is divided by the mass. Just as field strength gives G tells us the force per unit mass. Okay, so this is the gravitational field strength. Okay, so you can compare this with gravitational so this is gravitational field strength, tells us the force per unit mass at a point in a field. So this is G is equal to F over M. Similarly, GPE divided by M is the gravitational potential. The symbol used for potential is phi. Okay, in the beginning of the chapter we saw this letter phi. It's PHI, phi. And unit mass means 1 kilogram. Gravitational potential is defined as follows. Again, very important, these definitions. Also, you can go to the glossary and see the meaning of this word, so that you have a better understanding of what it means. The gravitational potential at a point is the work done per unit mass in bringing a mass from infinity to that point. So from deep outer space where there is no gravitational field, this object is brought towards the surface of the planet, or in this case we can say the Earth, for example. Okay, the gravitational potential at a point is the work done per unit mass in bringing a mass from infinity to the point. Now you can see there is a negative side, because what happens is, without the negative side, if you consider, the gravitational potential energy increases, because the value of gravitational field strength increases when it comes from infinity close to the surface of that planet. But we have a negative side here to indicate that that value is becoming more and more negative. Okay, more and more negative, because if you look at this equation, when the height becomes less and less, the gravitational potential energy becomes less and less. Okay, so it becomes more and more negative, means it becomes lesser and lesser. Okay, so that it matches with this. Okay, we will see. The gravitational potential at a point is the work done per unit mass in bringing a mass from infinity to the point. For a mass m, we can write an equation phi at a distance r from capital M. Okay, so here we have the G is the universal gravitational constant, also called the gravitational constant. Notice the minus sign. Gravitational potential is always negative. This is because as a mass is brought towards another mass, its GPE decreases. Since GP is 0 at infinity, it follows that anywhere else GPE and potential are less than 0. That is, they are negative. Okay, so you should know this equation. Now when we go towards the end of this chapter, also in the summary you can get this equation. Okay, so we'll have a look. Summary. Oh, they haven't given it. Oh yeah, it's here, sorry, it's here. The gravitational potential of a point mass is given by this. Okay, so in all the chapters, it's very important that you go through the summary and also the glossary. Now, previously we saw gravitational field strength, gravitational potential energy. Now we can look at gravitational potential. Gravitational potential. See, gravitational potential. Okay, we saw gravitational field, we saw gravitational field strength. We didn't see gravitational potential energy on these two. Okay, so the gravitational potential energy, the energy a body has due to its position in a gravitational field. Gravitational potential, so this divided by the mass will give you gravitational potential. The gravitational potential energy per unit mass at a point in a gravitational field. Okay, so gravitational potential energy, this value divided by the mass is the gravitational potential. Now you can see this is the energy due to due to its position in a gravitational, here also at a point in a gravitational field. Okay, let's go back to the lesson. Okay, so this paragraph is important. Okay, again notice the negative sign. Gravitational potential is always negative. This is because as a mass is brought towards another mass, its GPE decreases because the height decreases. The distance between the center of the surface of the earth and the center of mass of the object decreases. Now if you are considering the earth and an object, okay, its GPE decreases since GP is 0 at infinity. Now again, if you go to infinity, it is 0. So when you come closer and closer to the surface of the earth, it should decrease. But so what happens is the negative value decreases. It follows that anywhere else GPE and potential are less than 0. So that's why more and more negative. They are negative. Picture a spacecraft coming from a distant star to visit the solar system. The variation of gravitational potential along its path is shown in figure 18.18. Okay. We will concentrate on 3 parts of its journey. As the craft approaches the earth, it is attracted towards it. Okay. Because the earth's gravitational field will attract the aircraft as it has a mass. it is attracted towards it, the closer it gets to the earth, the lower its gravitational potential energy becomes, and so lower the potential. So the lower its potential. As it moves away from the earth, it has to work against the pull of the earth's gravity. Okay, it has to work against the pull of the earth's gravity, because when it's moving away, the earth is pulling it. So when it's moving away, it has to do work against the pull of the earth. Now when it is falling to the earth is doing work in bringing it down to the earth, in pulling it towards the earth. But when it is going away from the earth, it has to do work against that pull of the earth's gravitational field. Okay, so its GPE increases, and we can say that its potential increases. Okay, so you can see over here, when it's going away from the earth, it has its potential increases. Okay, so it becomes less and less negative. But when it's coming towards the earth, it becomes more and more negative, because work is done on it. But when it's going away, it has to do work against the gravitational field of the earth. So its potential increases or becomes less and less negative. Okay, so make sure you don't confuse this. You can go through it again, so you'll have a better understanding why it's always negative. Why, when it is now clearly you know, when the h increases, when the height increases, the gravitational potential energy increases. When the height decreases, the gravitational potential energy decreases. So that is clearly happening over here, but with a negative sign. So more negative means less gravitational potential energy. Less negative means more gravitational potential energy. Okay, so it's always negative. Okay, so we can see again with the example of the sun. Okay, see, first we'll go through this. The earth's gravitational field creates a giant potential well. You can see here, that is like the well, giant potential well in space. We live at the bottom of that well. Now we are living on the surface of the earth. We are living at the bottom of the well. Our height from the surface of the earth is 0. So we are at the bottom of that well. As it approaches the sun, now this same spacecraft, it is attracted into a much deeper well, because the gravitational pull of the sun is much greater. So the gravitational field strength of the sun, G, is much greater than the earth. The sun's mass is much greater than the earth's, so its pull is much stronger, and the potential at its surface is more negative than on the earth's surface. Can you see? The potential well here is deeper than for the earth, because the sun's mass is greater. Now you know from this equation, G equals Gm over R squared. The greater the G, the greater the gravitational field strength. Okay, the gravitational potential is 0 at infinity, far from any mass, and decreases as a mass is approached. Okay, so here are some questions. Make sure you do all these questions. We'll go through this example. Okay, first, before we do that, let's go through these terminologies, the meanings of the words. The words used to describe gravitational and other fields can be confusing. Remember, field strength tells us about the force on unit mass at a point, because G is equal to F over M. Simple G, the gravitational field strength, is equal to F over M. So it's force on a unit mass. Potential tells us about potential energy of unit mass at a point. Okay, so if you remember the definition of gravitational potential, you will see gravitational potential energy of a unit mass at a point. Then you have already learned about field strength in connection with electric fields, where it is the force on a unit charge. So capital E is equal to F over Q. You remember when you learned about electric fields, you learned two equations for electric field strength. E equals F over Q and E equals V over D. So F over Q, electric field strength, like gravitational field strength, electric field strength is given by force per unit charge. Similarly, when we talk about potential difference between 2 points in electricity, we are talking about the difference in electric potential energy per unit charge. You remember V is equal to W over Q, capital V, okay, electric potential, okay, or the potential difference is equal to work done divided by charge, work done per unit charge. So similarly over here we have gravitational potential phi is equal to the gravitational potential energy divided by mass. Okay, to help you understand this better, I will write the equations and show you. Now again, if you go through this part, when we talk about potential difference between 2 points in electricity, we are talking about the difference in electrical potential energy per unit charge. Okay, that is given by this equation. Okay, the potential difference is electrical potential energy per unit charge. Okay, so work done is energy transferred, work done in moving the charge is equal to the electrical potential energy gained by the charge. So over here this is what we have. Now similar to this one, we have this. Okay, again over here if you look at this, electric field strength is given by force per unit positive charge. Okay, so it's force over charge here, that is electric field strength. Similarly, gravitational field strength is force over unit mass. Here it's unit charge, force over unit charge. Here it's force over unit mass. So we are comparing the two. This is for electric field, this is for gravitational fields. Here electric field strength, here we have gravitational field strength. Okay, that is what is explained in this paragraph over here. Then over here also you can see, when it comes to electricity, we have the potential difference is equal to work done divided by charge, unit charge. So it's work per unit charge. Similarly we have electric potential. So here this is gravitational potential, sorry, this is electrical potential difference. Here we have gravitational potential. So that is, again you can see here, this is energy, work done is energy transferred. So here we have gravitational potential divided by mass. So here we have divided by charge, divided by charge. When it comes to the electric fields, here we have, in the case of gravitational fields, we are dividing by mass. Okay, so to help you understand this better, now you can see this is the definition. But if you look at the equation that they have given about electric potential, you don't see anything about gravitational potential energy divided by the mass in this equation. For gravitational potential, this is the equation that they have given. So you don't see a mass division over here, but I will show you to help you understand it better. Yeah, so to help you understand it better, okay, so I will use this Newton's law of gravitation equation, and now here we have the force. Okay, then what we can do is we can use this equation. Work done is force into distance moved. Now this is work done is equal to energy transferred. So we are trying to get this over here, okay, what is in the numerator. And then if you divide, okay, so what I did was divided both sides by m. Alright, so what I did here was you know, we have this equation. So f times d, the distance, we'll say it's r. So f times r, I'm explaining this so that you will have an understanding of how you get this equation. Like over here it's the energy over mass, but the definition says this, but for phi you have this. So how did we get this? Okay, so we can do it this way so that you can have a better understanding of the equation. Okay, so you can see work done is force into distance moved in the direction of the force, and I divide by mass, like what we have done here, gravitational potential energy divided by mass. So this is the gravitational, this is the energy divided by the mass. So over here this is the force, so force times the distance. Now let's say the distance is r, so I multiply this by r, and that's what I have done here, and then I divide by m, okay. So when we do that, we should get phi, the gravitational potential. Okay, then I simplify, 1 r here cancels out with 1 r there, and m cancels, and I put a negative sign because when it comes from infinity towards the the body, let's say for example the earth, the gravitational potential energy and gravitational potential becomes more and more negative, because work is done by the earth on that object when it comes towards the surface of the earth from space. Okay, so when you simplify, you get this equation, which is what you have here. Okay, so that way you have an understanding of how come the definition is this: gravitational potential energy divided by unit mass, but gravitational potential is given by this. So this is where you can remember it. All right, we'll continue. Okay, let's go through this example. A planet has a diameter of 6,800 kilometers and a mass of 4.9 into 10 to the power 23 kilograms. A rock of mass 200 kilograms, initially at rest and a long distance from the planet, accelerates towards the planet and hits the surface of the planet. Calculate the change in potential energy of the rock and its speed when it hits the surface. Okay, first thing is write down the quantities that are given. R, the radius of the planet, plus the distance from the planet to the surface of the planet, right? Accelerate. Okay, so long distance. So first, before that, R is, all right, this is the diameter of the planet, so you have to get the radius. Now what happens is this rock is far away from the planet, and then it comes to the planet. So when it comes to the planet, we assume that it comes to the surface of the planet. Now actually it is coming to the surface of the planet, towards the planet, and it hits the surface of the planet. So just at that moment when it hits the planet, the distance between the rock and the planet is the radius of the planet. This is the diameter. So we find the radius, and the mass of the planet is given. So we use this equation. Phi is equal to minus gm over r. Okay, that is giving us the gravitational potential. We learned it previously. Gives the potential at the surface of the planet, that is the gravitational potential energy per unit mass. Okay, and I told you gravitational potential, okay, this is equal to gravitational potential energy per unit mass, and I showed you how where to get this equation. Okay, so we have minus gm over r squared, that is the gravitational potential per unit mass at the point. So the gravitational potential energy of the rock of mass m at that point is given by this one. Now this is the gravitational potential energy. Now how come we get this equation? Okay, so again, if you go back to my derivation, okay, so this I showed you, if you multiply, okay, we'll show that. Okay, as you can see here, now first thing is to find the work done. Work done is force into distance moved in the direction of the force. So already we have the force here, and I multiply it by r, the distance. Okay, so that's what I have here. I multiply by r, and then I get minus gmm over r. Now how come this minus? Because when the object is coming towards the planet, when the rock is coming towards the planet, its gravitational potential energy becomes more and more negative. That's why we put this negative sign. Okay, so you can see here one of these r cancels with one of these r, then you get gmm over r, which is what we have over here, minus gmm over r. So that's how you get this. Okay, anyway, in the previous derivation I already showed this step. Okay, now you can see if you divide this by the mass, by m, you will get minus gm over r, minus gm over r, which is the gravitational potential. So gravitational potential energy, this divided by the mass will give you gravitational potential. Okay, so we are supposed to find the change in potential energy of the rock and its speed when it hits the surface. Now change in gravitational potential energy using this equation, the GPE of the rock when it is far away is 0. So calculate the value. The value we calculate using the equation gives the decrease in the gravitational potential during its fall to hit the surface. Far away it's 0. So this will give, you don't need to find initial and final, because initial value is 0. So then this is the final value, which is actually giving you the change in gravitational potential energy. Okay, so substitute G is the universal gravitational constant, also called the gravitational constant. Then M is the mass of the planet, and this is the mass of the rock. So capital M for the bigger mass, simple M for the smaller mass, divide by the surface at the, now this is when it's at the surface of the planet. Okay, so then surface of the planet means from the center of the planet to the surface of the planet. So that will be R. This is the diameter, so you have to get the radius. Okay, so substitute, then you will get this. Now what happens is, in the beginning the rock is at rest. So what is happening is, once it hits the ground, now initially its kinetic energy is 0, and then it is pulled towards the surface of the earth. So its gravitational potential energy becomes less and less and less, and what is happening is, when it is when the rock is brought towards the surface of the planet, the gravitational potential energy of the planet decreases and the kinetic energy of the planet of the rock increases. So the decrease in gravitational potential energy, which is this, is equal to the increase in kinetic energy. Okay, so what we can do is we can set the two equations equal to each other, and we can find the kinetic energy, which is equal to the decrease in gravitational potential energy. So this is the gravitational potential energy, this is the kinetic energy. Then substitute, and we will get V equals 4400 meters per second. Note that the rock's final speed when it hits the planet does not depend on the mass of the rock, because even if you use mgh over here, that m cancels out. Okay, so let's say you set this equation equal to this one, then the simple m's cancels out. So that's why they say, note that the rock's final speed when it hits the planet does not depend on the mass of the rock. This is because if you equate the two equations for kinetic energy and change in gravitational potential energy, the mass of the rock cancels. Okay, I already showed you that. So very important. So you can actually note down these equations. I can send you this one. Okay, then the last bit, orbiting under gravity. For an object orbiting a planet, such as an artificial satellite, artificial satellite is a man-made satellite, like the Hubble Space Telescope. Natural satellite is a natural one, like the moon. Okay, the moon orbits the earth, so it's a satellite, but it is a natural satellite. Okay, so for an object orbiting a planet, such as an artificial satellite orbiting the earth, gravity provides the centripetal force which keeps it in orbit. In the previous lesson, previous chapter, the chapter before this one, we learnt about circular motion. Then we learnt about centripetal force, centripetal acceleration. Centripetal force is always directed towards the center of the circle, and centripetal force can take different forms. Now if it's a planet, if it's a satellite orbiting a planet, then it is the weight of the planet or gravitational force on the planet due to the gravitational force of the planet on the satellite, or we can say the weight of the satellite due to the planet. That is the centripetal force on the satellite. Okay, that's what keeps it in orbit. This is a simple situation, as there is only one force acting on the satellite, the gravitational attraction of the earth. So this is what I explained. So this force F is the centripetal force. It is also the weight of the planet, weight of the satellite due to the planet. We can also say it is the gravitational force on the satellite due to the earth, due to the planet. The satellite follows a circular path because the gravitational force is at right angles to its velocity. Okay, so here you see gravitational attraction of the earth provides the centripetal force on an orbiting satellite. Okay, then this was the equation we learned previously for circular motion. Now you can see this is the gravitational force, and it is also given by this equation. What we learned in this lesson today, the gravitational force is equal to the Newton's, over here we saw that, Newton's law of gravitation equation we are using over here. So that force is given by this equation. Okay, and this is also equal to the weight, the gravitational force on the satellite due to the earth, and that is also equal to the centripetal force. Okay, so this is the weight of the satellite due to the earth. We equate the two, then what happens is we simplify this. 1r here cancels out, then m and m cancels out, so you will get v squared equals gm over r, and there is no need of a minus sign here, as the gravitational force and the centripetal force are both directed towards the center of the circle. And using this equation you can calculate the speed of the satellite. Satellite must travel to stay in circular orbit. Okay, so yeah, now if the speed, now this is the speed that by which it orbits the earth. Now if this speed is greater than this value, it will go out of the orbit. If this speed is lesser than this value, it will fall into the earth. So that satellite has to maintain this speed so that it orbits the earth. Like I said, if it's greater, it is too fast, so it will go out of the earth's orbit, out of the earth's gravitational field. It will go out of the orbit, out of the satellite's orbit. If it's too less, it will fall into the earth. So this equation allows us to calculate, for example, the speed at which a satellite must travel to stay in a circular orbit. Notice that the mass of the satellite m has cancelled out. The implication of this is that all satellites, there is no simple m here, no mass of satellite. So the implication is that all satellites, whatever their masses, will travel at the same speed in a particular orbit. You would find this very reassuring if you were an astronaut on a spacewalk outside your spacecraft. You would travel at the same speed as your craft, despite that your mass is a lot less than its mass. The equation above can be applied to the planets of our solar system. M becomes the mass of the sun. So we can apply it to the planets also. So if a planet is far away from the sun, then its velocity will be lesser. The speed will be lesser, because greater the r, the lesser will be the the speed. But also if the mass is constant. Okay, so greater the mass, again the smaller, larger the r, then this also has to increase or decrease so that it equals this. You would travel at the same speed as your craft. Okay, so yeah, so we went through this. You can see the picture. During the spacewalk, both astronaut and the spacecraft travel through space at over 8 kilometers per second. Okay, here is an example. The moon orbits the earth at an average distance of 384,000 kilometers from the center of the earth. Calculate its orbital speed. The mass of the earth is 6.0 into 10 to the power 24 kilograms. So we can use this equation. Write down the quantities that are given. G is given to you. It is a constant, no need to memorize it. And the mass of the earth, because this is orbiting the earth, so we need the mass of the planet that the satellite is orbiting. So this is the mass of the planet we are using over here, mass of the earth. The moon is orbiting the earth. Okay, then r is the distance from the center of the earth to the center of the moon. Okay, so they have already given that, an average distance from the center of the earth. So they have given this already. So simple, substitute, you will get the answer. Make sure everything is in SI unit so that you get your answer also in SI unit. So the moon travels around its orbit at a speed of roughly 1 kilometer per second. So it's a very high speed, but this is in a vacuum, no air resistance, so it can go at that speed. Even here you see 8 kilometers per second. It's moving so fast. Okay, then we have orbital speed. So make sure again you do these questions. It is often more useful to consider the time taken for a complete orbit. The orbital period t, since the distance around an orbit is equal to the circumference 2 pi r, it follows that now you are getting this equation from the circumference and the time to go around the circumference of the circle. Okay, you know speed is distance over time. Okay, so we are using the equation speed is distance over time. Now since it's a circular orbit, it's, let's say it starts somewhere there, it goes all the way around. So the distance all the way around is 2 pi r, and the time for one complete orbit is the period, that is capital T. So that's why we get 2 pi r over t. Okay, see 2 pi r over t. But we also know that v, the orbital speed v, is given by this gm over r, that is v squared. V squared is equal to gm over r. So first thing is we can square both of these. V squared is equal to 4 pi squared r squared over t squared. Okay, then that is v squared. So this is actually, we are squaring both sides first. So v squared is gm over r, and you make t the subject of the equation after that. So this side is equal to, once you square this side, that is v squared, and v squared is equal to this. So that's how you get this here. Then t squared is equal to 4 pi squared r cube over gm. Okay, this equation shows that the orbital period t is related to the radius r of the orbit. The square of the period is directly proportional to the cube of the radius. Okay, you can see that here this is a constant, pi is a constant, g is a constant, m is also a constant. So t squared is proportional to r cube. The square of the period is directly proportional to the cube of the radius. This is an important result. It was first discovered by Johannes Kepler, who analyzed the available data for the planets of the solar system. It was an empirical law, one based solely on experiment, since he had no theory to explain why there should be this relationship between T and R. It was not until Isaac Newton formulated his law of gravitation. Okay, so you know the law of gravitation equation, F is equal to G m1 m2 over R squared. Okay, this one. That it was possible to explain this fact. So we showed it over here now using that equation. We derived the other equations and got this. It follows from this equation. Okay, so once we have this now, natural satellite, I told you, moon, artificial spacecraft, and a lot of debris. Each of these satellites uses the Earth's gravitational field to provide the centripetal force that keeps it in orbit. In order for a satellite to maintain a particular orbit, it must travel at a correct speed. I told you about this already. This is given on page 278 also. It follows from this equation that the closer the satellite is to the Earth, so lesser the r, the faster it must travel. So if r is less, this should increase. If it travels too slowly, it will fall down towards the Earth's surface. I told you that. If it travels too quickly, it will move out into a higher orbit. Okay, so we have this equation over here which we get from this. Okay, that is that one. Again, if you want, we can look. Yes. Then again, there are more questions. Then here they are telling you some uses of these artificial satellites. Many are used for making observations of the Earth's surface for commercial, environmental, and meteorological or military purposes. Others are used for astronomical observations, benefiting greatly from being above the Earth's atmosphere. Still others are used for navigation, telecommunications, and broadcasting. Figure 8.11 shows two typical orbits. Okay, so here we have an elliptical orbit, and then here we have a circular orbit. A satellite in a circular orbit close to the Earth's surface and passing above the poles completes about 16 orbits in 24 hours. Okay, so we call this actually a polar orbit. Okay, so there are different satellites. We have geostationary, we have polar. Later on you will learn this. 16 orbits in 20. As the Earth turns below it, the satellite sees a different strip of the Earth's surface during each orbit. That is actually this satellite. Okay, it's going like this. So it completes 16 orbits in 24 hours. Okay, so because of that, you see a different strip of the Earth's surface during each orbit. A satellite in an elliptical orbit has a more distance view of the Earth. Okay, so that is that. Now this geostationary orbit is always facing the same part of the Earth. Therefore it has the same period as the Earth. So let's say if it's facing United Kingdom, then it will always be facing the United Kingdom. So when the Earth turns this by a certain amount, it also travels by the same amount, because it has to always face the same part of the Earth, because it's a geostationary. Geostationary, you know what geo means, what stationary means. It's facing the same part of the Earth. Therefore it will have the same period as the Earth. Okay, so here it says that the satellite remains above a fixed point on the Earth's equator. This kind of orbit is called a geostationary orbit. Okay, so here it remains above a fixed point on the Earth's equator. There are about over 300 satellites in such orbits. They are used for telecommunications, transmitting telephone messages around the world, and for satellite television transmission. A base station on Earth sends a TV signal up to the satellite, where it is amplified and broadcast back to the ground. Satellite receiver dishes are a familiar sight. You will have observed how in a neighborhood they all point towards the same point in the sky. If you look at the satellite receiver dishes which are fixed on top of the roofs of houses, you will notice that in a certain neighborhood they are pointing in the same direction, because the satellite is in a geostationary orbit. The dish can be fixed. Okay, but in the case of an orbit like this, that dish has to move. Okay, so for example, when it's when they are getting the weather forecast, for example, let's say here it doesn't need to move because it's a geostationary satellite, so the dish can be fixed. Satellites in any other orbits move across the sky, so that a tracking system is necessary to communicate with them. Such a system is complex and expensive, and too demanding for the domestic market. Geostationary satellites have a lifetime of perhaps 10 years. They gradually drift out of the correct orbit, so they need a fuel supply for the rocket motors which return them to the geostationary position. So you know, we learn this equation. Now if the speed changes, then it will go out of the orbit. So again, there has to be some fuel to bring it back to the orbit and maintain that speed. So they need a fuel supply which return them to the geostationary and which keep them pointing correctly towards the Earth. Eventually they run out of fuel and need to be replaced. We can determine the distance of a satellite in a geostationary orbit using the equation. So you know, the period is the period of the Earth. If it's a geostationary satellite, then mass of the Earth we know, g we know, so we can find the distance of the satellite in that geostationary orbit. And they are doing this. For a satellite to stay above a fixed point on the equator, it must take exactly 24 hours to complete one orbit. So the period is known. We can make r the subject of the equation, like what they have done here. R cube is t squared gm over 4 pi squared. Substitute the values into the equation. G m mass of the Earth. The period you have to convert it to seconds. Here it's given in hours, 20, so this is in seconds. Then you get the distance, 4.23 into 10 to the power of 7. Okay, this is from the center of the Earth, because r, you know, we take from the center of the Earth to the center of mass of the satellite. Okay, and this also, remember, geostationary satellite is directly above the equator. Now previously I said directly above UK, but it should be directly above the equator. And then this is the radius of the Earth. So when we subtract this number from this, we get how far it should be from the surface of the Earth. And you can see in terms of the Earth's radius, how many times this is. Okay, so the orbital radius is 6.6 times the Earth radii from the center of the Earth. So what you do is divide this by this, then you would get 6.6, or 5.6 Earth radii from its surface. Okay, so when you subtract this from this and divide it by this, you will get 5.6, because that is when you subtract this from this, you are getting the distance from the surface of the Earth to that satellite. Okay, figure 8.12 has been drawn to give an impression of the size of the orbit. Geostationary satellites are parked. Now you see, this is the equator. Here you can see it's shown. Are parked in the Clark belt, high above the equator. This is a perspective view. The Clark belt is circular. Okay, so we have come towards the end of this lesson. Make sure you go through the summary. It's very important. We can go through it quickly. The force of gravity is an attractive force between any two objects due to their masses. The gravitational field strength G at a point is the gravitational force exerted per unit mass on a small object placed at that point. That is G equal F over m. We already saw this. The external field of a uniform spherical mass is the same as that on an equal point mass at the center of the sphere. Okay, so go through those. Then Newton's law of gravitation, I told you should know the definition. Then the equation of Newton's law of gravitation, we saw that already. The gravitational field strength at a point is the gravitational force exerted per unit mass on a small object placed at that point. Already we went through this also. We went through all of this. And I told you about uniform gravitational field. G is constant in a uniform gravitational field, and it's equal to the acceleration of free fall. And we talked about gravitational potential at a point is the work done in bringing unit mass from infinity to the point. Then we also saw this. Then period is the time taken for one orbit. The orbit period can be found by equating the gravitational force. And we saw all of that. This equal to this. And we got this equation. The orbital speed of a planet or satellite can be determined using the equation. Then finally we learned about geostationary satellites that have an orbital period of 24 hours and are used for telecommunications, transmissions, and for television broadcasting. Okay, so make sure you go through the theory, go through the summary, do all the questions in the brown boxes so that you have an understanding, minimum knowledge to answer the past paper questions. After doing those, you can start working on the end of chapter questions, or you can go to the do the questions from the past paper books, which has those solutions, the ones you got from me. And then you can do the questions in the drive also. Again, those are all questions arranged by topic with the answers or with the solutions. Okay, so that's the end of gravitational fields.